So for a change, I'm going to talk about a purely experimental work and mostly based on observations. And this work was possible thanks to my excellent collaborators, Soumen Das, who was a PhD student of my colleague Sankar Ghosh. Soumen is now in Okinawa Institute as a postdoc, and also our collaborator Julian Klamze from France. And this work is now, the preprint is on this archive. Now, the title involves this term, time reversal symmetry breaking. So let me first explain what do I mean by this in this context. Let me just recall things that you already know. So let's look at a trajectory, particularly in the phase space, and also look at a trajectory exactly the same but going backward. Then for deterministic systems, if both trajectories are governed by the similar dynamics, then it's time reversible. But if you go for the stochastic systems, you say that the system becomes time reversible if in some stationary state, if the probability with which I would see the forward trajectory and the probability in which I would see also the backward trajectory, if they both are the same, then the state is time reversible. So this, as you all very well know, happens for systems in equilibrium. So even the system is in equilibrium, the system is still exploring its phase space, so that it has evolution being in the equilibrium. And if you look at those trajectories and look at their probabilities of forward and exactly that of the backward, the probability occurs with the same probability. The trajectories appear with the same probability, and it's a consequence of detailed balance condition. And one simple way of, quantitative way of measuring this breakdown of time reversibility is to look at this quantity. So if you take the log of the ratio, if the two are equal, then this would just become 0. But if you take for systems where this reversibility is broken, particularly for non-equilibrium stationary states, if you look at this average, this is a positive quantity. It's also known as the Kullback-Leibler divergence between the two probability distributions. This is also known as the average entropy production for a system in outside non-equilibrium stationary states. One of the interests in this quantity comes from that people often think of this as a measure of the irreversibility in the system. And there's been a lot of works, particularly there is a nice review type of articles by Yariv and Julia in this Nature review. Now, 10 years ago, or even probably there were works earlier, but people got interested in the context of the active matter. And this work is quite well known now, that where they try to say that if you measure exactly this in the context of active matter and measure that Kullback-Leibler divergence, it can tell you how far a system goes away from criticality, away from equilibrium. And there are several such articles. There's this roadmap article, which is also written by Sriram. It talks about such direction. Now, often the difficulty in all of these are mostly theoretical works, and the difficulty comes is that measure requires the high dimensional information about the whole phase space, so it's often very impractical. There's this works of Dov-Levin and Chaikin, where they try to propose a numerical algorithm also measuring such quantities. Now, our motivation came from this simple question that if I want to measure such measures of irreversibility in an experiment, could I have something very simple that would be experimentally measurable? It would be non-invasive, and I should be able to do it in absence of any observable flow, such that where the non-equilibriumness is not so obvious. And this is what we do. And the idea is extremely simple. So we say that often in the active matter system, if you're looking at particle-based active matter systems, then you just look at the collision events. So if you see the two particles, and then there is two kinds of angles, incoming angles or outgoing angles. If the trajectory of the system is in a time reversible state, probability of these two will be the same. And if it is not, then the probabilities of incoming and outgoing would be different. You can define the similar way a Kullback-Leibler divergence that will measure just this, how much the system is breaking time reversibility, one kind of measure. And it is indeed possible, and in order to demonstrate that, Sankar cooked up or devised an active matter system, which is also very simple. You just take a sphere, and inside is a motor, and the motor runs, rotates, and as a result, the sphere rolls. And as it moves on the floor, because of instabilities, it will wiggle. And as a result, you will see a trajectory which for a while it moves persistently, then changes, and again moves. So which is essentially the characteristics of active kind of particles. And you can indeed do these measurements. You can try to find this probability of these incoming and outgoing angles in every collisions. For example, this is for just a single particle, and you measure collision events with a boundary, and you would find that they are different. You can think about two particle systems and look at the collision, binary collision between particles. You will also find the differences. And in this way, you can try to, in a way, quantify that given the system under different kind of conditions, how much is it breaking the time reversibility, okay? So the one point was that depending on which environment you put the system, you will find different values of this breakdown of time reversibility. Now, one question comes that isn't it obvious that if you look at the active matter this system, there will be always an energy flow because it's drawing current from the motor and then using it to self-propel. So it would be obvious that it's a non-equilibrium system. Now, if I look at this system under different condition, wouldn't just by measuring the amount of current that is drawn, wouldn't I just say that how much it is away from the, that's, at least the data shows that that's not so obvious. Even in this context, just look at the black and white curves. These are in the context where I look at the collision of two particles, one happening in the bulk, one happening near the boundary, and they have very different values of Kullback-Leibler divergence. But if you look at their instantaneous current just around the collision event, you can't see much of the difference. But you would be able to see the difference if you measure the amount of current that the motor is drawing from the battery, if you measure it over a very long period of time. And so this is what you do. So you measure the energy extraction from the motor over a long period of time. And now you want to find out how much of this really the energy is going into moving the particle. So often in active matter, one interest would be that the internal energetics, which actually makes it active and breaks the lethal balance. So you'd be interested in how much of the energy that the internal degrees of freedom uses in order to make it move. So in this context, if we want to see how much of the battery energy goes into moving the particle in the translation motion, so what we did is the following. We first took the ball and take the motor out. So the motor is rolling, but it doesn't let it roll. So you have no translational motion. And there, of course, you would find that this energy current has a distribution. We find the mean value, and then now we couple the ball with the motor, and if we now leave it, it will roll. So if we subtract the mean value, it will now count how much of the energy it is using in order to move the particle. And if you plot that distribution, it has this following shape, which is non-Gaussian. Now this distribution has a very surprising symmetry. That is, you can observe. And this observation says that if you look at the ratio between the positive and the negative, it follows such kind of distribution. And this distribution reminds very much that of something called a Galovetti-Cohen symmetry. If you take the two different temperature baths and measure the energy flow, then you find the more the temperature is different, this exponent is larger and larger. And as a result, this gives you also a measure of how far a system is away from equilibrium. And you can do these measurements, and you can show that under different conditions, if you put this active matter system, you can say when the system is, how much is away from the equilibrium by measuring how much is breaking the time reversibility. And I will just leave with this last point, is that even in this experimental system, you would like to see some large collective behaviors, which are usually very difficult, but the effect of non-equilibrium you can demonstrate in some kind of simple collective behaviors as well, and which is this. So on the left-hand side, this black one is only active ball. Rest are just passive balls left around. And what is found, the typical configuration is that all the passive balls are surrounded in one side, and the active ball is making around it quite empty. And this, it turns out, if you do a numerical simulation, it appears in somewhere in between that of the dissipation, and if the dissipation is very small, it becomes highly mixed. If it is very large, all the passive particles goes near the boundary. And this I leave you with this movie, just to show you that you can see some effect of the non-equilibriumness even on a macroscopic behavior driven by only single active particle system. Okay, so with that, I thank you for your attention.
You had this trajectory where it suddenly changes the direction, right? I think third or fourth.
Right.
Somewhere you had.
Yeah, it's coming.
Yeah. So this is a single particle, right? It goes and changes the direction completely. And why does it happen in this case?
So there is a load, and it is happening because of really the mechanical instability. So there is also the floor, which is not perfectly smooth. And also there is this load which is swinging around a rod. And at some point, the rod just, so lever also tilts. And some point it tilts so much that so you see if the rod is rotating like this with this load, it's moving this side. And if it flips it, it just goes back on the other side. Okay. And this flipping is induced by some instabilities.
So this remind me of this thing called direction reversing active Brownian particle, which I worked with Urna and this thing, where my question is basically, can you have a better statistics for this kind of trajectories, like the distribution, position distribution, etc., on a free space?
So, free space we did not.
Or even in a harmonic potential, I don't know how are you going to, maybe in
so we did try that. So we put it on a platform which is like this, and then try to see. We have histogram data, and
we have some calculation for both the free space and the harmonic potential, and I mean it would be nice.
So you see, I showed you a numerical. So for the numerical result, we have a stochastic differential equation which roughly captures the behavior. But we didn't do any theoretical analysis, just mostly observations and data analysis and the numerical simulation of a model system. Yes, Urna. Yes. So you see, there is a persistence length and there's a persist time. I have to go into the details, but there is indeed a time scale, which is certain parameters in the problem determines that, which are easier to say it in the stochastic equation which we are modeling. It's easier to write it in terms of those parameters. But here there is a well-defined persistence time.
The integrated current distribution which you had shown, was it for a single sphere or many of them?
It's for a single sphere.
Oh, this is for a single sphere. Okay.
So the Galavati coherent comes out even for a single sphere. And the main point was that often when you look at active matter, the fact that the system breaks the active matter non-equilibrium comes due to the energetics. And there would not been much of studies of those because it was very inaccessible. The system was initially generated with this idea that I will have some idea or some control over how the internal energetics is used to self-propel. And it's, at least in this example, it shows that even that internal energetics has certain thermodynamic characteristics, even for such athermal system.
And the case where you were subtracting the mean, turning of the motor, that was also for a single particle?
For a single particle.
So you mentioned this Kullback-Leibler divergence, and that has the ratio of probabilities of forward and reverse trajectories. And the Martiniani paper mentions that measuring that probability is very difficult.
Yes.
And they propose this using cross-parsing complexity.
This one?
Yes.
Yes, of course. And so they look at a slightly very different quantity. They look at locally just how many particles are coming and going, and with certain directionality.
Yeah. And you were not interested in the local entropy production.
So we are not interested in locally at some, like a space.
Space, yeah.
But we have, when I showed you the data, we can separate out the collision events that's happening inside the bulk or happening near the boundaries. And we can separate out how much of the KLD is different. So this is kind of the two graphs. One is in the happening collision in the bulk, one is happening near the boundaries. And you would see that there is a different values.
Okay, and here you're using the ratio of the probabilities themselves.
Yeah, we are measuring everything in terms of probabilities. Okay. Yeah, we have, and it's much more accessible. You don't need like what in those papers where you need some information theoretical measures and fancy algorithm. Here you don't need any of this. It's just very simple measurements. You can do all this.
I thought this would be difficult, but nice. Okay. Thank you.
Any other questions? I have a question. What is meant by non-invasive measures? What is
non-invasive? So what I meant that usually when one standard way to measure this where the system is outside equilibrium, you measure it through how much the fluctuation dissipation relation is broken. Now, in that way, when you try to measure, you have to perturb the system. So that is invasive because it's also sometimes problematic because non-equilibrium systems are very susceptible to tiny bit of perturbations. So you would like to have a measure where you don't have to perturb the system. And this is one such measure. That's what I meant by non-invasive. Here we don't touch the system. We just observe with cameras, and that already gives them. There is one.
Yeah, it's a good faith question.
Sure.
So where is the statistical mechanics here exactly? Because it's an athermal system and there is a certain stochasticity in the way the ball is rolling. But maybe you could elaborate on that a little bit.
So you see, if you take any Markov processes, then for the finite, at least for finite Markov chains, which has a stationary state, you can show that this symmetry that I'm showing will come out rather obviously. There's nothing very fancy about it. As soon as you break the detail balance. And this symmetry for discrete Markov chains is very straightforward.
And so what is the entropy connection to the Markov?
So it's not the thermodynamic entropy, but what is used is that when a system is outside equilibrium, it is somehow generating entropy. So simple analogy is this. When you look at the system coupled between two reservoirs, if the two temperatures are different, then you see this heat is going from here to here. So there is entropy, it's losing from hot reservoirs, entropy gaining to here or increasing. And because of the two temperatures different, the system to be in its non-equilibrium stationary state, there is a constantly entropy difference and that is essentially considered as an entropy production. If you try to describe in a much more dynamical point of view or Markov processes, you can define those Kullback-Leibler divergence and show that there is certain relation with this.
Just
Depends on
just a small question. Yes. You mentioned about perturbation. So is there any chance that stochasticity induces perturbations in any way? Is there a possibility?
Possible, but in this case, what I only meant by that, we don't disturb the system. We just observe with a camera and let the system evolve by itself.
Yeah, but you mentioned stochasticity in the system, built in the system. So is there internal stochasticity? Is it possible for the internal stochasticity to induce perturbation in the system? That's my question.
I'm not clear, but I can talk about it later. Yeah. It will, yes. If you put more and more, it will not be just the interproduction, will not be the sum of interproduction of each particles, but because of the interactions, the interproduction will also change. And there will be contribution that also due to the interactions. So that in this case, a characteristic of this particle is that the environment actually affects its internal degrees of freedom, which is not typical for the standard models of effective matter. Left and the right is only this viscous damping. So this gamma term. That's all that you change. Where it turns out that our experiment that we are doing represents somewhere in the mid region.
Catch him during the break.
Sure.
Yeah. Thanks, Tridib.